All right, so it's 3 minutes past the hour. I think we can start now. Just to let you guys know, you're all on mute, and we really appreciate it if you could stay on mute for the duration of Professor Olm's presentation. If you have any questions for Professor Olm, please just put them in the Q&A bar in the lower right, and then we'll direct those questions to him once he's done presenting. That'll be about 30 to 40 minutes into 30 to 40 minutes past the hour. So with that, Franz, feel free to begin when you're ready.
Okay, thank you very much, Andrew, and thank you to all of you who made it today, June 25. I'm going to speak about resilience for sustainability, and the topic has been a hot topic in the Concrete Sustainability Hub for quite some time. But I think everybody today understands very well what the resilience or the absence thereto means for us all in the light of COVID-19. Before I get started, I would like to dedicate this talk to two dear friends of the Concrete Sustainability Hub and personal friends, Bill Larson of Cal Portland and Tom Shismadi from Lehigh Cement, who have been instrumental of pushing this topic in the CSH Hub. The work which I'm going to present is not my own work. It is actually the work of a large group with my former students and present student, Dr. Jake Roxon, Benzumanaf Elivatiotis, Talal Muller, Konstantinos Karamides, and Tina Vatsiotis. Further, the advisors, my colleagues who helped us advise this work, Randy Kirchen, Jan Magnon, Roland Palanque, and Katarina Ioannidou, for the later tour from the CNRS in France. So let's get started here with the question which we all want to address is, what is actually resilience? And since we are now in this online mode, I thought I'm going to start with some drawings about it. How do you define resilience? And, since we are a little bit quantitative, we're going to make an XY plot here, where we put on the y-axis a performance of a system, a structure, an economy, social equality, and on the x-axis we put time y. Well, we are at a certain stage initially, and then an extreme event happens. And you know exactly when this happened for COVID-19, and the system drops down in terms of performance. This drop here has to do with the robustness of a system, robustness. But the robustness, if it's robust, of course, the drop will be less. But if such a system comes down, there's a second part, a very important one. What is the recovery? And the recovery would be either to the same level or a higher level. So wherever you would like to have it. And the question is, let's say, how fast are we able to bring this back to the same or higher performance of the system? Well, very important here is for all of us in this current crisis, as you ask yourself, is the time to recovery. Time to recovery. And this is a very important topic for all of us. Currently, we know exactly what that means here in the current crisis. But what I would like to share with you today are the results which come out from this thinking of resilience in terms of building stock and national building stock, as well as the community scale and at city scale. So don't worry, I will not write with my bad handwriting further on, and will continue with my presentation. So here you see the graph in a perfect shape. So resilience, in essence, is the time it takes to bring a system after an extreme event back to same or higher performance. The systems which we consider are cities, buildings, structural, non-structural elements of buildings, all the way down to construction materials. Otherwise said, it's a true multi-scale approach. And the events which we consider here are hurricane, earthquakes, precipitation, flooding, and fire. So our focus of research into resilience in the CSH Hub goes from the building scale to the community scale and to city scale. to address a critical thing. What is the return of investment if we invest in resilience of the building stock? So the topics I would like to touch today on is one, give you an update on where we headed with hurricanes. The hurricane season just started a couple of weeks ago. And in the past presentations on this topic, I hope I was able to convince you, if you were there, that city texture matters critically when it comes to the response at the city scale of building performance. The second one, which is closely related but goes away from the pure wind load, is precipitation flooding, which very often comes with these extreme events. Here, the key question is how to quantify the flooding in terms of or the damage caused by flooding due to the time of flood exposure, and we want to address this also in relationship with city texture. Finally, I'm going to address a topic of high importance for many of you, which is fire, high temperature exposures of buildings, be it for safety reasons, when you are a firefighter or an inhabitant of a building, or whether it is at a community scale, where you ask yourself, will there be a spread of fire? And if you look at the bottom of the slide, you find sort of the order of magnitudes of dollar amounts which we are talking about per year, which, given the current crisis, we won't be able to sustain for many years, to continue to sustain damages on the order of $200 to $300 billion a year during hurricane season, flooding, and in terms of fire, 50 billion losses per year, and associated expenditures. So with this in mind, let me start with the first topic, which is hurricanes, from city texture to social impact. And the question which I ultimately want to address is the socioeconomic impact of hurricanes and how one can reduce it. To start out with, to make this point clear, where did we come from to this texture here? What this slide shows you, actually this video, which I'm now going to start, are simulations of the hurricane category 4, which hit in October 2018 Mexico Beach, destroying a large amount of buildings. The hurricane was a category 4 with wind speed 130 and 150 miles per hour. And as you see in this video here, this is the boundary condition basically here coming from the sea. That's a hurricane 4. But as you go into the city, you find out that actually much of the wind speed here inside those cities is amplified far beyond a category 5, actually moving all the way to much higher wind speed. So you readily understand that from this slide that the texture, how we build a city, plays a critical role when it comes to evaluating the risk of damage to a building through a hurricane. Well, in fact, to make this clear, what is the particularity of our approach? The current approach, which is used in design codes, is basically the design buildings for a wind pressure P, which scales with the wind speed to the power 2, which is the wind speed, the far field wind speeds, which are codified, for instance, by the American Society of Civil Engineers, and then multiplied by rho is the density, but most importantly here is the drag coefficient CD, and often taken in our normal design as a single building for evaluation of this pressure. This pressure is then used to design the building. What we propose here is actually to consider, in addition to the far field wind speed, the effect of city texture of a building which is in a certain environment, in its first shell. In fact, as we found out by this study, is that this city texture actually can magnify the wind loads for which buildings should be designed by a factor as much as 5 times of what the current design codes require. Now, the approach here is, after much work, actually comes down to evaluating this drag coefficient in the following form, which has two terms in there. One is the classical term, which is currently in use, this part here. The other one is the city texture effect. And that city texture effect actually has to do with the dimensions, of course, of the building or surrounding buildings, particularly the local scale. But most importantly here, two factors which come from city texture analysis, which is one, CN, which is called in statistical physics the coordination number, basically referring to the number of neighbors, and R is the first shell, basically the environment in which your building takes place. And this data is available and can be calculated for each building by means of using the information about building stock readily available on the internet. So to make my point here, if you look sort of just at for Mexico Beach, if you just look at the drag coefficients of these buildings in Mexico Beach and evaluate which of those buildings should have failed because the amplification due to this drag coefficient related to the texture it was much higher, you basically can cover something like 67% of accuracy here of the actually damaged buildings. Meaning that the relevance of this approach is evidenced by the observation that pressure amplification due to city textures are significant. More importantly, you can ask yourself also, what would happen if I now start redesigning the city? And in fact, you're looking at taking out buildings and looking how the neighboring, so the number of neighboring buildings would start, and how would that ultimately affect the drag coefficient. So you see we have buildings here on the left side. We taking out a number of individual buildings, so to reduce the number of neighboring buildings, and by doing so, the drag coefficient reduces. In fact, you may want to see this as a damage curve. If a building is destroyed, what are the other buildings subject to, and why is not everything destroyed after hurricane? In fact, the key question here, which comes out from these simulation, is that we can either think about redesigning our cities, which is unlikely because we cannot reduce the density of the cities in much way, but more importantly, thinking about how to design our building stock more safely by taking into account these city texture effects. In fact, you can do this not only for Mexico Beach, but you can apply the same type of approach at the states level, actually for the entire United States, if need be, or particularly in those areas which are prone to hurricanes, and evaluate here the risk level of the building stock at the state scale. So here, for the example, for Florida, you basically see here in green those buildings which are designed basically to code. So one would expect that those buildings are well designed for the type of with the right pressure, given the current drag coefficient used for design buildings. However, you find out in yellow, you see that the drag coefficient may be 50% above the current norm, which means that we definitely under design the buildings, that they have a much higher risk of failure. And in red are those buildings which have more than 50%. So with this type of approach, with this condensation of the phenomena of the drag coefficient, we can develop this map which take into account in a detailed fashion the risk for each individual building and building blocks due to hurricane wind speeds amplified by city texture. And you see that some neighborhoods may be at much higher risk of damage. You see it here in red. Many other buildings will not be. So there is a clear impact here, which the high-risk buildings should definitely be prioritized for resilience, retrofits, or eventually considered for premium home insurance plans. Otherwise said, there needs to be some action in order to retrofit our building stock to reduce this high risk of damage due to city texture effects, the way how we like to live and build our building stock. But what are we missing here? We haven't talked yet about the building itself, the what happens to each one of those buildings, and that's a critical information as we bring the topic back to resilience and want to know what is the time to recovery. So we need two more information. One is the damage inventory for each individual building, and the other one is then a link with the bill of activity in order to identify the benefits of mitigation by resilience enhancement. So let me start with the damage inventory of building. And we have developed in the Concrete Sustainability Hub here an approach which allows us to not only see, as it's shown here, structures fail under an extreme event, and here it's the example of an earthquake, but actually developing from this approach the so-called fragility curves. So fragility curves here, which consider all the different building specific components, including structural and non-structural members. In fact, an example here of our approach here is illustrated here in this five-story building. We discretize the structure in terms of masses and put all the information which we need in the bonds, so in the connection where the beams, walls, windows, roofs of the system. Here, the example here considers a core or not. I'm going to show you some simulations with a core in order to develop a quantitative means of determining what is the risk of damage from probabilistic point of view to these structures. So my first structure here I want to show you to illustrate this approach is a typical reinforced concrete structure which has interior walls, a building envelope, and so on. And what the approach actually does is we probe all possible connections and see which one are the one most likely to fracture given a certain load which we have in the system, so damaged. And you see here in different colors, you know, the failure of the interior walls, some elements of the building envelope, but the building core here for this concrete structure is completely untouched. If we compare this structure here with a wood structure, also with a core, things somewhat change. So you see again here the development of these broken links, which basically provides the damage inventory. But you see immediately that simultaneously with the building envelope and the interior walls, there are large failure even touching the building core. So despite the fact that both structures were designed for the same maximum load, you see that given these wind loads, we are able to quantify here the likelihood of damage to structural or non-structural members. Just as a last one, what would happen if this was a wood structure without core? We would actually, so here what the interior walls would be still non-structural, but the building envelope here also non-structural, but with walls in there. You basically find out that how the structure fails. This is not a structure you would design, of course, in this form. So you have a high level of damage. All this here allows us then, you know, qualitatively classify, you know, for reinforced concrete structure, wood without structural core for this particular example, from no damage to high damage of the system. But more quantitatively, we did all these which comes out from simulations into fragility curves, which expresses the probability of exceeding damage in the building. And if you take here this probability of exceeding for any type of value, so horizontal line into the system, you will find that the inventory, the one which is first touched is the wood, until it comes to reinforced concrete structures. Otherwise said, we can synthesize into material-specific building type fragility curve the information and use them for different buildings and integrate them, the failure of non-structural and structural members. Now, with this in mind, we can then take it to the next level and connect this damage inventory with a link, by linking it with the bill of activity, while considering that after an extreme event, there's a demand surge, simply due to the fact that you don't have enough a carpenter to work on repairing the work, so that the prices simply go up. And combining the damage inventory on the one side with this bill of activity provides us for each building a means of evaluating the benefit if we were to mitigate this year by resilience enhancement. This is some work done by Ipek Benzomanaf in the CSH Hub, so which basically integrates the following thing. One is the hazard risk, and that's simply the probability of occurrence of a hurricane. Already what is done currently is the consideration of surface roughness or terrain, which is there. But in addition, what we now consider here is this urban texture effect with which I started today. Finally, we determine here the structural response for each of those buildings, right? And then look, what would be the means of retrofitting these structures in order to improve and reduce the damage of these buildings by means of the fragility curves, by changing the fragility curves from one solution to a retrofitted solution. What turns out here is, if we consider these the city texture approach is so this texture informed approach is that the statewide benefits which would result by mitigating the damage quickly increases. So for instance, in the classical approach, if one were to use it with classical tools, so without considering city texture, there would be, for the state of Florida, maybe on the order of 2.6 million homes will have a payback within 1 year, and the total statewide benefits would be on the order of $4.8 billion per year. By contrast, if you consider the texture informed approach, such an investment actually has a much higher return, because it both at the state level as well as for individuals, as statewide benefits are up to almost $20 billion a year, and we're talking about 4.2 million homes have a payback within 1 year, given the high level of risk of hurricane. We can take this all the way to the state and basically look here at the benefits of mitigating hurricane damage by means of this resilient enhancement, to map then here at the state scale the dollar amount which households obtain, and you can identify then the areas where mitigation would have the highest impact in terms of financially for individuals. Otherwise said, there's a clear socioeconomic value of mitigating for individuals, for the smaller community, the cities, the towns where people are, but as well as the state scale. A similar approach which you have now seen for hurricane can be applied to precipitation flooding, which is the next research project we had started on last year in September, looking into the impact of city topology and texture related to precipitation flooding. Now, just a word about the classical approach, how precipitation flooding is typically addressed and commercially available as solutions, it is based on so-called shallow water equation in most cases, and consists of following the floodings or the height of water over terrain in time and space, considering all these different issues like the 3D terrain network, soil condition, permeable, non-permeable, structural objects, bridges, pipework, etc. But this would be for a very particular city or area in order to determine what is the risk of flooding. It is critical if you're looking into urban flash floods, for instance, where you need to know, where you have to take into account the relatively short time of the precipitation, which entails, for different reasons, a flood locally in a city. Now, what we are looking at is slightly different. What we are interested here is into the damage, to evaluate the damage and estimate of the damage, where we look at the time of the flood exposure. The longer the time of flood exposure occurs, the more damage it will do to the structure. So a key question which our approach looks into is how much is flooding reversible and irreversible in terms of close to equilibrium conditions. And the approach which we develop here in the hub is based on what's called density functional theory, which is a technique which was actually developed for nanoscale adsorption processes. The idea basically is that you put a material in contact with an outside bath defined by some chemical potential, and you ask yourself where in the at the small scale structure will this outside liquid gas adsorb and develop from this here so-called adsorption and desorption isotherms. Now, we adopt a similar type of approach for the flooding problem by analogy, by considering all types of features relevant for this problem of precipitation flooding. Meaning, we're interested in buildings. We consider, of course, the terrain, the topology of the terrain, of the city terrain. We consider drainage systems, soil type, whether they're low, high permeable, and so on. So what we do here, basically, we apply an outside precipitation source to the system, and the simulation technique determines where water will accumulate at equilibrium for each precipitation rate applied. Now, this allows us then to determine, well, what we have coined flooding drainage isotherms. So I want to give you and walk you through these here because they have a high information about the water damage, which relates, for instance, here an example where you have insufficient drainage. A very simple example here. So you have a terrain here, you apply a certain precipitation rate, and you see here this accumulation of water as you would expect at equilibrium. That's not the point. The real point about this here is in terms of these isotherms, where this normalized flood height basically here is followed in two ways. Well, the first way is the filling up. So when you increase the precipitation rate, you see here the start of water accumulation, and then this increase here in steps. These steps, by the way, I believe have to do with the coarse discretization of the overall domain. So I believe they will be quite continuous. Then at some point you will basically drain this water, so going the opposite direction by reducing this outside source, this precipitation rate. And what you then realize actually that the end of drainage here at this precipitation rate is much to the left side from where the water accumulated. So what that actually tells us, because it's equilibrium-based simulation, that the water damage with which we have to count, so long-term exposure of a structure of the building stock by water here, is defined here in terms of these flooding drainage isotherms. So another example, just to contrast it here, to get used to these flooding drainage isotherms at a city scale, neighborhood scale, is the example here where you have a pipe, so typical drainage system. We have, the pipe starts filling up. Once the pipe is full, and then of course you start having here this increase on the surface, right? So how does that look here? So we start up with the filling. You have the start of water accumulation, and you see here this filling process here. And then as you drain, you actually realize that the end of drainage, even though it's much more to the left than the start of accumulation, the difference in between for this last step is relatively small, meaning there's really no water damage to be expected. So what these flooding drainage isotherms thus provide at the scale of a neighborhood, of a city, hopefully in a city, once we have done all these simulations, is a means to evaluate it, of evaluating the risk of damage for the building stock in a community at the neighborhood scale, and then at the city scale. Let me finish my talk to talk about what we have done on fire, also exactly with the same type of approach, which consists of asking the question, how fragile is a building actually due to long-term fire exposure? To motivate this here, we all know the fire risk here of buildings. The key factor are temperature rise, which are more or less well known and codified. For instance, the cellulosic fire curve, which is there. Second element of it is the structural response of the system. And here's a picture from FEMA, which shows that because some softening that occurs in the outside columns, at the end, the building load will lead to some buckling of the phenomenon. But this very phenomenon actually may differ whether this is a concrete or wood building or any other type of structure. As you see here in this simulation, I will come back to them in a little while in order to specify what they allow us to obtain. So what are the key factors actually which define fire safety for such buildings? So let me start with wood. Charring typically occurs at 300 Celsius and above, which propagates inside the material. That's what we typically always think about when we worry about wood, because it's the charring phenomenon. But there are many other phenomena actually which occur at a material scale, which is a material softening behavior, which means that the strength and the stiffness of the elements degrade substantially, independent of the jarring, but in function of the temperature. In addition, very critical for wood structures is the softening of the connector resistance when they are exposed to fire. When it comes to concrete, we have the equivalent of the charring would be the thermal spalling, which is the phenomenon that when concrete is exposed to high temperature, it kicks off layers very similar like the onions, the layers of onions around the material, thus reducing the effective section actually of the system. In addition, it undergoes material softening, so a strength decohesion and a stiffness reduction, what we call thermal damage here, which you see here, which are more or less well understood here. If you compare, for instance, the Young's modulus or the stiffness with a reference stiffness at 20C, you see this decline here with high temperature, so high temperature exposure of materials as one can find in a laboratory. So how do we account for that here in our approach? Similar to what I showed you before about the molecular approach, about the wind loads, we're using molecular dynamics, potential of mean field type approach, where we discretize a structure in terms of mass points at some equilibrium configuration, its initial state, and just describe one thing, which are the interactions here between these different mass points by stretch potential on the one side and bending potentials in order to capture bending elements in such structures. And of course, the key information for these potentials are type of material and the type of structural use or structural element they are taken into account. So to show you this here, this interaction potential, let me start out with concrete spalling. What is actually what needs to be taken into account? So as I've already mentioned, one of the key phenomena of concrete exposed to high temperature is this spalling phenomenon. It typically is that the propagation of this spalling front occurs between 250 and 400 Celsius. And what it effectively does, it reduces the effective section of a structural element. But there's another phenomenon in place which actually states that the remaining column is subject to thermal softening, meaning that the stiffness and the strength goes down. So how do we account this actually in the simulation? You see on the right side a typical moment curvature relationship of such a reinforced concrete section. The points are experimental points. In red, you see the way how we model it, typically using tools of potential of mean field. Here, a Morse potential. At the bottom, you have the integral of this curve, which basically gives you this potential. Now, when you subject it to temperature, with these two phenomena involved, what de facto happens is two things. Well, one, this moment curvature capacity goes down, and with the initial slope is representative of both the reduction of the effective section of the material, but as well of the softening behavior of the material, as well as a reduction in the maximum curvature such a beam can take. So what we do actually is the effective section properties, which scale the interaction potential, account for at the sectional scale for this thermal decohesion and for damage. Now, a similar approach can be developed, or we have developed for wood. If you replace spalling by charring and take into account the particularity of heat transport through a charred layer, plus the softening behavior at the material scale, you would have an equivalent approach for wood. But the one thing which is different between concrete and beton, or very critically different, are the wood connections. And the wood connections, which you see here, for instance, a nail connection, but you can have the same thing for a bolted connection, where you see on the right-hand side sort of this reduction as the bolt temperature increases. In essence, the resistance of the whole connection goes down, and quite significantly, particularly when you are above 200, 300 Celsius. So this is the really main difference, as we found out, in the behavior conceptual wise between the two materials. Otherwise, they are just material properties. Now, how does that actually affect the problem? So you see here, what is the input? The input is basically this temperature curve. And you see here in Celsius, the temperature as a function of exposure time, the cellulosic fire building according to ISO 834. You see in a relatively short time, the temperature is well above 500, reaching, it actually never reaches an asymptote here. But you see, you're very quickly above the 300 degrees, which is relevant for wood connection, or the 250 to 400, where the spalling of concrete occurs. Now, the simulations actually allow you then here, if you look here, to see immediately how these structures actually behave and accumulate damage due to this long-term fire exposure. So what I show you here on the right side is sort of the condensed information from the simulation, which is the frame damage, which provides here the stability of the structure for this wood structure and for this concrete structure, both structures having been designed exactly for the same type of ultimate limit load. As you can see, the wood frame fails early, and particularly here due to the connection failures, while the concrete frame buckles at a later stage once the spalling has reduced the section to a level that it cannot carry anymore the dead weight of the remaining structures. Otherwise said, these exposure time frame damage curves uh, have the potential to become a reference curve for each type of structure to define the fire fragility curve of a building, and basically address the rating, the fire rating of structures through this probability-based approach, which looks into the frame damage induced frame damage or structural damage induced by long-term fire exposure. Some key takeaways which I want to leave you with, then I would take off questions you may have. I hope I was able to convince you about the power of this multi-scale approach to go from material to structure, neighborhood, city, state, that just getting stuck on one scale may not be the right approach to approach resilience. There are concrete solutions out there as part of resilience mitigation efforts, which have a significant benefit for owners of buildings, for inhabitants, for communities, and for states. There's a true socioeconomic meaning to enhancing resilience at the building scale all the way up to the state scale. We are there on the same route for in our developments towards flooding and fire, where I showed you today a new approach how we aim at quantifying the flooding induced damage by means of these flooding drainage isotherms. And I hope next time I will speak to you, I will be able to show you maps of cities, bring it to the same level as where our work on hurricanes ended. And finally, I showed you some first results about a physics-based approach to fire resilience safety of buildings subject to long-term fire by means of these fire fragility curves, which flooding and fire needs to be integrated with the corresponding economics model to evaluate economic resilience of structures. What's in the making? We're still looking at hurricane resilience enhancement. I think as we all can't wait that this COVID-19 crisis will be over, we all know that there will be a need for federal and state stimulus packages. I think it's a good time to push now for science-based resilient enhancement, as we cannot afford uh, 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 this type of damage, both financially and socioeconomically wise. On flooding and fire, we have an approach in place. The proof of concept has been given. We're now going all the way to neighborhood city scale with city texture features and integrate them with the economics model. With this, stay safe and well, and stay connected with us. If I can answer a question, I will be happy to do so. And thank you very much for your attention.
All right, thanks, Franz, for the presentation. We've got one question in the chat bar right now, which is, does charring of wood depend on the species? Does plywood or cross-laminated timber char at lower temperature due to the resins, glues, and other organics included in their makeup?
Yes, charring definitely depends on it. The speed, actually, the speed by which the charring front propagates. In fact, there have been numerous studies out there who have looked into this here. The problem is a front propagation problem, which is driven by the amount of combustible material at the charring front. So it scales directly here with the type of material which is there. That's one effect. The other point about charring, I think, let's say we all have in mind the charring as the because from our barbecues, we have in mind that charring is the dominating feature when it comes to the resilience of buildings with regard to fire. While it is important, we believe that the connectors are the much more critical one. In fact, charring, if you have a char on a surface, it slows down because of the temperature, which has to propagate through the charring front. So charring is not the most critical one when it comes to structure. Of course, it is critical for burning, for fire spread, no question about it. But when it comes to the structural stability, the connectors are, I think, the Achilles heel of wood structures.
Let's see. So the next question is, oh, before I answer this question or pose this question, I'd just like to say that this webinar is being recorded and it will be edited and then posted online and forwarded to everyone who has attended. So don't worry about missing any content. It'll be forwarded right to you. And with that said, here is the next question that's been posed. Do you think the current building codes allowing tall wood structures have accounted for the connection failure you've described?
So that's a I think look, the building codes express two things: the current state of the art and the efforts of each industry to make sure that their material is well represented. So I think the state of the art here, that's what we address specifically with this type of research. So if you take it from the point of view of the maximum load capacity for which a structure is designed, absolutely the design codes are right. But as I've shown you, the design codes do not consider city texture. So for that purpose, the buildings would need to be correctly designed for much higher pressure. Is this a design code or is this a local regulation which a city can require because it's a local effect? I think that is to be debated. But as we bring these results forward and show the importance of city texture effects, connectors, I think there will be a need to address the design practice, whether this is at the scale of the design codes or whether this is at the local local city scale in order to properly account for the particular texture of a city. That is a question of implementation.
One more question we have is, what about bolt failures under fire?
Yes, that's actually, this is a very interesting topic, actually, which I know. So bolt, this is basically this graph here. So it's not from us. Basically, I looked sort of into different literature. There's a very interesting phenomenon here. So what this graph shows you the reduction basically of the strength of a connection in function of the bolt temperature, which people have measured. So as the bolts quickly reach the temperature, they are directly exposed to it. You see that there happens very quickly a reduction of the resistance to almost 50%, up to 100 Celsius. So that, which is basically immediately whenever you have a fire. It then stabilizes until 200 C, and then all goes the way down to 300. Some people say there may be some residual strength here at 20% of it. But you see 300 Celsius. You need to put this 300 Celsius in connection with the temperature rise which one would consider for such a design. So 300 Celsius is here, right? So we're talking about a couple of minutes. In the game, you basically start losing those connection, unless you extra protect them with extra layers of, and you name it. And now that's something which there may be some solutions out there, so that these connectors will be, of course, much more bulkier. They will not be as elegant as they are currently and used in the wood industry. bowl temperature reaches after a couple of minutes the 300 Celsius, which means from what experiments has shown, uh, we basically have lost this connection. And this is what we find out in the simulation. So you see here the wood, how quickly it fails. The reason for it is primarily the failure of this wood connection.
So one more question we have is, what parameters and features are the most important for developing city texture for flooding? How is it different from hurricanes in the input data for the models?
Yes, so the critical yes, there are quite a few actually. The 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 key factors of in addition to city texture will always be there. You have here a third dimension, and the third dimension is the terrain. Number one. Two, you have a drainage system, basically pipes. Rivers, etc., which classically do not affect or the impact on wind speed is rather negligible if you compare it to the problem of flooding. So the texture effects, that's what we aim to study. We don't have the result yet here, but we have the same type of approach in place where we're going to consider neighborhoods, characteristic city textures. The new elements are characteristics which relate to the terrain, topography, and to the drainage system. These are the two quantities which come in addition.
And then one more question is, since the building code has a probability of collapse inherent in the design provisions and concrete exhibits much lower probability of collapse at the design loads, are wood structures under design, or do concrete structures have excessive capacity?
So look, from an engineering design perspective, uh, if you just use the current code decision, both have the same, they are subject to the same load. So do now, and then the design happens. Can one define then with regard to this pressure that concrete structures are over designed? I don't think so. What our results show is that they ultimately lead to have another value. They have an additional value, a resilience value. And this is a key message, I think, which I want to leave you with, which is resilience is not equal robustness. Design codes designed for robustness, but robustness is just a drop of performance. What concrete has is this additional resilience, and for that reason, these fragility curves, or the enhanced the fragility curve, these improved fragility curves, help actually to add a resilient value, which is currently not covered by design codes. So I think the debate about design code is everything is all about robustness. I think we need to bring it forward to show the value of resilience for our societies and bring this into the realm of engineering and design of structures.
One more question we have here is, in defining resilience, in addition to time and level of recovery, would the socioeconomic impact be an important variable to consider? If yes, how to weigh it in the resilience measurement?
Yes, so this is, I don't have yet the results. So what I hope that Benzo will show me shortly is to connect actually these maps which we showed about the risk of the the maps of higher pressure, to try to correlate them with census data on income levels. I think that type of information would be helpful to answer this question. I don't have yet the information. What I have currently only is what would be the return of investment if I go from structure by adding into it, so it's resilience enhancement of the structures, and showing that with this approach one can identify the, the the return on investment for at the level of a building, so owner, to the level of a city. I think there's more still to be discovered there related to socioeconomic impact, by which I mean if a family with a $50,000 income compares with a family with $200,000 income, and you compare the return on investment or the benefit in thousands of dollars, it has a complete other order of magnitude. I think it is there where it's definitely worthwhile to see to identify this benefit with regard to the income level of these houses. That's work which is feasible thanks to census data. I hope I will be able to report this to you soon.
One final question we have here is, in the context of hurricane resilience, what is the effect of urban forests and trees, and can we modify the building envelope to improve the friction coefficient?
Oh yeah, so any obstacle, of course, will always hold it back, right? So there are two effects to having these barriers. So whether they are natural or forest, etc. One would be to reduce the exposure to winds. That would be a natural one. But then there's the second one, which is what if they'll become projectiles? And basically hitting then the building. So I think that is sort of that's a very interesting topic, I think, which urban planners need to consider when planting and choosing the type of species of trees to plant in a city or building forest there. But definitely all type of systems which create a higher level of disorder, and that I mean now here from in terms of irregularity in a grid, and forest city first would be precisely that, can reduce actually the wind pressures on buildings.
All right. Well, with that, thank you everybody for attending. We really appreciate it. A recording, as I mentioned, of this webinar will be available to all of you, and not just the attendees, everybody who registered. And that recording will be on our YouTube channel and will be publicly available. So you can expect to see that in the next few days. So again, thank you very much for attending. And we hope you can join us next time for further public webinars in our series. So have a great Thursday, everyone. Bye.
Thank you.